Hello everyone, welcome back to Matrix lecture series. In the last lecture, we started a new topic, transpose of a matrix. Today, we are going to discuss the symmetric and skew-symmetric matrices. Let's get started. In the last lecture, I have already explained you the definition of a transpose of a matrix, the properties, these examples I have also discussed with you. I hope you might have understood those examples. In case you have not, then you can write it in the comment section. Okay, now let's begin today's discussion with this symmetric and skew-symmetric matrices. First comes the definition that what is symmetric and skew-symmetric matrices. In simple language, a symmetric matrix is one in which the matrix, my original matrix and transpose matrix, if they both are equal, then it will be a symmetric matrix, right? And obviously it should be a square matrix, because if it will not be a square matrix, then in that case the original matrix and the transposed matrix, they can never be same, right? If I have a square of say length 2 meter and breadth 3 meter, if I transpose it, if I rotate it, then what will be my resultant? It will be 3 by 2. Similarly, in matrices, if I have a matrix of order 2 by 3, then the resultant order of my matrix will be 3 by 2. This will be the order of my transpose matrix. If I have the matrix of order 1 by 4, then the resultant transpose matrix will be of order 4 by 1. So they can never be same, right? If the order are not same, then how can even the matrices can be same? So obviously the matrix should be square matrix, right? So I have explained you the definition of a symmetric matrix. Symmetric matrix is one in which the original matrix is same as the transpose matrix. Okay, fine. Here is the example also. In this example you can see that if you transpose it, let me transpose this matrix. Okay, A transpose, what will be the A transpose? This row will become a column, that is root 3, 2 and 3. This row will become a column, that is 2 minus 1.5 minus 1. This row will become a column, that is 3 minus 1 1. Now examine A inverse, so not A inverse, A transpose and A, are they both same? Let me erase it. Yes, now check, are they both same? Yes, they are same. Therefore we can say that transpose and the original matrix are same, hence we can conclude that it is a symmetric matrix. I hope it is clear to you. Okay, here is a denotion, a way in which it is denoting that Aij will be equals to Aji, right? Okay, I hope it is clear. Now moving ahead to next definition of the skew-symmetric matrix. Skew-symmetric matrix in simple language is one in which the original matrix is same as the transpose matrix, just a small difference of a negative sign, that is this. Okay, in my transpose matrix it is same as original matrix, just a difference of -1. This is how we define the skew-symmetric matrix. Okay, now a very one important point is written here, that in all the skew-symmetric matrices, all the diagonal elements are 0. This is a very important question which is very often asked in board as well as CUET exam, that what type of matrix should always be a skew-symmetric matrix? A matrix in which all the diagonal, remember, all the diagonal elements will be 0, that will be a skew-symmetric matrix. I hope it is also clear to you. Here is an example also. If I have such a matrix, you can very well see that all the diagonal elements are 0, so you can very easily, without wasting any time, you can report that yes, it will be a skew-symmetric matrices. If someone asks you to identify whether this is a skew-symmetric or not, then you can very well see that all the diagonal elements are 0, hence it will be skew-symmetric. This is a way in which you can identify whether the given matrix is a skew-symmetric or not. let's try to see some similar result or similar pattern in symmetric matrix also. Okay, if you see in the symmetric matrix, this row and this column are same, right? If suppose if I try to write it in general, okay, let me write in general. If I have here as ABC, then the same BC will be here. Okay. If I have some element DE here, then I will be having E here and a different element F here. So basically, if you see this element, this and this element, this and this element, they are same. The elements on the main diagonal, all of them are different. That is, one conclusion you can draw from here is that in a symmetric matrix, all the diagonal element, if you suppose if some matrix is given to you and you are asked that whether it is a symmetric matrix or not, then how you will approach it? You will see that whether all the elements on the diagonal, are they different, are they totally different? Yes, they are different. And then check that whether these corresponding remaining entries, are they same to each other? Yes, they are same, hence it will be symmetric matrix. In this way you can very easily identify and very quickly identify that whether the given matrix is a symmetric matrix or not. One thing that I also want to tell you, that every matrix is need not to be a symmetric or a skew symmetric. A matrix may be a symmetric or skew symmetric, or it may not be anything. It may be a simple matrix, just like our rectangular matrix, right? This is also a very important question which may be asked. The examiner can ask you that is a matrix can only be symmetric or skew symmetric? You will say no, the matrix can be skew symmetric, it can be symmetric, and it can be nothing of two. It can be simple matrix. The very classic example of this is a rectangular matrix, right? So you are now equipped with both the tricks of symmetric matrix and skew symmetric matrix. Again, I am repeating that in the skew symmetric matrix, all the diagonal elements are 0, and in the symmetric matrix the diagonal elements are totally different. The remaining corresponding elements, you cannot say actually the corresponding elements, but you can say some the analogous elements or these opposite elements, they are same to each other, and all the diagonal elements will be totally different. One example of a matrix which is both symmetric and skew symmetric is, you can yourself tell me, is a zero matrix, right? If this is my matrix, if I transpose it, what I will get? I will get 0 0 0 0 0 0 0 0 0, hence it is symmetric. If I find negative of A inverse, it will be negative of 0, which is nothing but 0. So I will get again this matrix, hence the 0 matrix is both symmetric and skew symmetric matrix. Now let's check whether the two tricks that we have identified, are they working on this 0 matrix or not. Let's see. Now let's first see the skew symmetric matrix. Since all the diagonal elements are 0, hence it will be skew symmetric matrix. Now let's see for symmetric matrix. If you see the corresponding, let me change the color. Okay, the opposite elements are same to each other, and the diagonal elements are different, but here they are not different, they are same. So we can conclude one more thing, that the diagonal elements should either they must all be equal or they must all be different. Got it? Now let's see some another example. Okay, let's try to look at some another example. If I have say here 3 1 3 1, here 2, here 0, okay, here 5, here also 5. Let me transpose it. Now why I am telling you this example? Because I want to make you able to yourself generate a result, or to yourself reach to a common general understanding. Okay, so see what will be the transpose. What will be the transpose? Let me check for the space. Okay, I can write the transpose here also. If I transpose it, I get 2 3 1 and 3 2 5 and 150 150. Check whether they are two same or not. Yes, they are same. Here the opposite elements, if you see, they are same. Okay, they are same. Yes, and in the diagonal, neither they are all different nor they are all zeros, but the two are same and one is different. What conclusion can we draw from three cases? What three cases? This one is this case, another one is 0 0 matrix case, the third one is this case. The thing that we can conclude, which is very important, is that the only requirement for a symmetric matrix is that these opposite elements should be same regardless what is on the diagonal. This is very important thing you need to understand. In the skew symmetric matrix, our concern is with the diagonal elements. All the diagonal elements should be 0. In the symmetric matrix, what the general result we have achieved by checking various examples is that our diagonal elements can be anything. They can all be different, they can all be equal, they can be equal and different at the same time, but the only requirement is that these opposite elements should be same. This is very, very crucial. Okay, this is how we generalize the results. I hope it is clear to you. Let's see this theorem 1. This theorem says that if A is some matrix, obviously square matrix, then A plus A transpose is symmetric and A minus A transpose is skew symmetric. We need not to do this proof, and this can be very easily verified using some example. We will see the example and see whether it is true or not. The thing that you have to keep in mind is that if some square matrix is given, then A plus A transpose is a symmetric and A minus A transpose is a skew symmetric matrix. One another theorem is that, and it is a very important theorem, and it says that any square matrix can be expressed as the sum of symmetric and skew symmetric matrix. Now this is important. Why it is important? I have explained you that if I have some matrix A, it can be symmetric, it can be skew symmetric, or it can neither be symmetric nor be skew symmetric. But the thing is that each and every square matrix can be expressed as the sum of symmetric and skew symmetric. Why we are able to have this? Because of this fact, because of this theorem. This theorem says, what does it say? I am again repeating, if A is some matrix, then this matrix, we can, with this matrix we can make a symmetric as well as a skew symmetric matrix. With this only single matrix we can find A transpose very easily and we can add them. So this will result in a symmetric matrix, and this subtraction will result in a skew symmetric matrix. Due to this theorem we are able to reach at this conclusion also. Actually this conclusion, that every square matrix can be expressed as the sum of the symmetric and skew symmetric. And how it can be represented? It can be represented just like this. This is a important thing that you need to remember. Okay, fine. Let's move to this example. What does this example says? In this example we are given the matrix B, and okay, yes, we have to express this matrix B as the sum of symmetric and skew symmetric. Now this is very easy. We are given with B. How we know that how we represent a matrix in a symmetric as a sum of symmetric and skew symmetric? In this way. what does this way tells? That add this, what does this addition gives me? This addition gives me a symmetric matrix. Add this, this subtraction will give me a skew symmetric matrix, and we have taken the half. Okay, you can make an analogy, you can actually understand it in this way, that half will become one complete. So in this way, this and this will be add up and this will cancel, so we are remaining with 2a, and 2 will get cancelled with this half, so we are remain with a. Hope it is also clear to you, right? So just simply what we have to do, we are given with B matrix, we have to find B transpose, then we will find B plus B transpose, and then multiply it with some scalar, with a scalar half, we get this, right? Similarly, we can find B minus B transpose and multiply it with half, we get this. Simply add both of these, the addition gives me this matrix, which is nothing but my B original matrix, right? Hope it is also clear to you. That's all for today. In case you have any doubt, you can write it in the comment section. You can also connect with us via various social media handles. Thank you.